Welcome to our presentation on panel and pool data analysis. This method is a powerful tool in modern econometrics. As eloquently stated by Baltagi, panel data's key advantage is its ability to control for unobserved individual heterogeneity, which are unique factors specific to each entity that don't change over time. Today, we will cover the theory, practical implementation, and a case study using EViews. For instance, when studying the factors affecting a country's GDP, unobservable factors like cultural work ethic or institutional quality can be controlled for using panel data methods, providing more reliable results. To begin, let's first understand what makes panel data unique by looking at its structure compared to other data types. This slide introduces the fundamental data dimensions in econometrics, comparing time series, cross-section, and panel data. On the left, a time series graph illustrates data for one entity, many years, focusing on changes over time for a single subject. In the middle, the panel data graph shows many entities, many years, highlighting its unique ability to track multiple subjects over time. The rightmost graph, cross-section, depicts many entities, 1 year, capturing different subjects at a single point in time. On the right, we outline why panel data is so valuable. It significantly increases the sample size and thus degrees of freedom, which enhances statistical power. It also effectively reduces collinearity among regressors, leading to more robust models. Crucially, panel data allows us to control for individual heterogeneity, accounting for unobserved unique factors that might otherwise bias our results. For example, in analyzing GDP growth, panel data combines information from multiple individuals or firms N over several time periods T to uncover dynamics that are invisible in single-dimensional data. This slide presents a roadmap for selecting the appropriate panel data model. We begin with our panel data structure. The first key question is whether we can assume homogeneous coefficients across all individuals. If the answer is yes, and we also assume homogeneous intercepts, then a simple pooled OLS model can be used. If coefficients are not homogeneous, more advanced methods are required. Assuming homogeneous coefficients, the next crucial step is to determine if we have heterogeneous intercepts. If yes, meaning each individual has a unique baseline, we must choose between fixed effects and random effects. This decision hinges on whether the individual effects are correlated with X, our explanatory variables. If they are yes, correlated, then we should use fixed effects, FE. If no, correlation is found, then random effects, RE, is more efficient. The definitive tool for making this distinction is the compass, the Hausman test. This test is the primary method for choosing between fixed and random effects. The rule of thumb states that if the null hypothesis of the Hausman test is rejected, meaning the individual effects are correlated with the regressors, then the random effects model is biased. In such a scenario, the fixed effects model must be used to ensure consistent estimates. This slide presents an overview of advanced methodologies and tools used in panel data analysis. We can divide these methodologies into distinct clusters based on their application. Cluster 1, focusing on policy analysis, primarily utilizes the difference in difference, or DID, method. As highlighted on the right, DID is considered the gold standard for causal inference, for instance, when evaluating the impact of a minimum wage increase. It allows us to compare changes over time between a treated group and a control group to isolate the causal effect of an intervention. Cluster 2 addresses long-run and macroeconomic analysis. This pathway often starts with panel unit root tests to assess the stationarity of our variables. If variables are found to be non-stationary, the next critical step is to test for panel co-integration. Co-integration, as mentioned in the Advanced Tools section, is essential for macro variables like GDP or consumption to prevent spurious regressions that can arise when trending data is used without proper handling. This naturally leads into the development of dynamic models, which often incorporate lagged dependent variables. Cluster 3 directly focuses on these dynamic models. These models are particularly important when the past behavior of a variable influences its current state. They frequently involve techniques like GMM, or Generalized Method of Moments, which is a robust estimation method for dynamic panel models, especially useful when dealing with endogeneity concerns. In essence, this map guides us from foundational policy evaluation techniques to sophisticated macroeconomic modeling approaches, ensuring that our analyses are both robust and theoretically sound. The slide presents the mathematical foundations for understanding the error component in panel data models. We start with the basic regression equation, YIT equals alpha plus beta XIT plus UIT. Here, YIT is the dependent variable for individual I at time t. Alpha is the intercept, beta is the coefficient, XIT is the independent variable, and UIT is the error term. The critical insight in panel data analysis is the decomposition of this error term. We break down UIT into three distinct components. UIT equals mu I plus lambda t plus nu IT. The first component, mu I, is the individual effect. This captures unobservable, time-invariant characteristics specific to each individual, such as a country's culture or a firm's unique management style. The second component, lambda t, represents the time effect. This accounts for unobservable factors that affect all individuals at a particular point in time, like a global recession or a widespread technological change. Finally, nu IT is the stochastic disturbance, which is the traditional idiosyncratic error term, representing random noise unique to each observation. The way we treat the individual effect, mu I, is what differentiates between fixed effects and random effects models. In fixed effects, we treat mu I as a parameter to be estimated, essentially as a dummy variable for each individual. This is appropriate when mu I is correlated with the regressors. In contrast, random effects treats mu I as part of the random error term itself, assuming it is uncorrelated with the regressors. The core difference between the fixed effects and random effects models lies in the assumption about the individual effect, mu I. The fixed effects, or FE, model assumes that mu I is correlated with the regressors XIT. It treats mu I as a fixed parameter, or intercept, to be estimated for each individual, effectively controlling for its influence. The FE model focuses on within variation, how changes in X over time for a given individual affect Y. This means we are looking within each group, country, firm, to see how changes in X affect Y. The random effects, or RE model, assumes that mu I is uncorrelated with the regressors. It treats mu I as a random component of the error term, rather than a parameter to be estimated. The RE model uses a weighted average of both within and between variation, making it more efficient if its core assumption holds. Its intuition is a weighted average of variation within groups and between different groups. This critical assumption about correlation is the deciding factor in choosing between the two models. The first and most critical step in EViews is to properly structure your workfile for panel data analysis. EViews needs to know which variable identifies the cross-section and which identifies the time period. You do this in the Workfile Structure dialog. You must select Dated Panel as the structure type. Next, you specify the cross-section ID series, which is the variable containing the unique identifier for each entity, like ISO code for countries. Then, you specify the date series, which is the variable indicating the time period, such as year. Failing to do this correctly will prevent you from running any panel estimation commands. To confirm success, look for the range description X cross-sections at the top of your workfile window. For instance, if you have data for 50 U.S. states from 2000 to 2020, your cross-section ID series would be the variable containing state names, e.g. state name, and your date series would be the variable for the year, e.g. year. Once the workfile is correctly structured, we can proceed to the estimation dialog itself. After properly structuring your data in EViews, the next step is to open the equation estimation dialog. This dialog is where you configure the specifics of your panel regression model. The image on the left shows the Panel Options tab, which is crucial for selecting your effects specification. Under Effects Specification, you'll find options for cross-section and period. Setting both cross-section and period to none will instruct EViews to run a pooled ordinary least squares, or OLS, regression. This approach essentially treats your panel data as one large cross-section, ignoring individual and time-specific effects. To implement a one-way fixed effects model, which is a common choice, you select Fixed for cross-section and leave Period as None. This specification accounts for unobserved, time-invariant individual heterogeneity. Below the effects specification, you'll see the coef covariance method. Here, white period is selected. This option specifies using White's period-consistent standard errors, which are robust to heteroskedasticity and arbitrary serial correlation within each cross-section, providing more reliable inference. The settings guide on the right summarizes these choices. None/none runs pooled OLS, and Fixed/none runs a one-way fixed effects model. It also mentions GLS weights, which are advanced options for correcting heterogeneity, such as using cross-section weights. Once your settings are configured, you simply click OK to run the estimation. We're now moving into our first practical case study, focusing on data preparation using the Penn World Table. Our scenario for this study is to analyze the relationship between GDP, denoted as Y, and population, or POP, across G7 countries. The screenshot on the left shows a sample of the data we'll be working with in EViews. You can see columns for the observation, the Y variable, ISO code for the country, and the year. You might notice some NA values in the Y column for CAF, indicating missing data points. This brings us to an important aspect of data hygiene. In panel data, a dataset is considered balanced if all units, or countries in this case, have data for every single time period. However, as we just observed, our data is unbalanced because there are missing observations. EViews is quite good at handling these automatically, but it's crucial for us to always check for any systematic bias that these missing values might introduce. For example, if a country consistently has missing data due to conflict, simply ignoring those observations might bias our results. This step of ensuring data hygiene is fundamental before moving into any estimation. After setting up your data, open the Equation Estimation dialog and go to the Panel Options tab. To run a cross-section fixed effects model, simply select Fixed under the cross-section dropdown, leaving Period as None. The equivalent command line syntax in EViews for this action is equation eq1.lscx equals f yc pop, where eq1 is the equation name, .lscx equals f specifies a fixed effects estimation for the cross-section, y is the dependent variable, c is the constant, and pop is an independent variable. This method is concise and efficient for scripting or advanced users. Remember, cx equals r would be for cross-section random effects, and pure equals f for period fixed effects. When interpreting the output of a fixed effects model, it's important to be cautious with the R-squared value, as it is often artificially high. Instead, focus on the t-statistics and f-tests to assess the significance of your variables and the overall model. To test if fixed effects are necessary, navigate to View, Fixed/Random Effects Testing, Redundant Fixed Effects. In the example shown, the p-value is 0.000, which is less than 0.05. This implies that fixed effects are necessary and should be included in the model. This slide demonstrates how to interpret the Hausman test, which is crucial for deciding between fixed effects and random effects models. We see the output from a correlated random effects Hausman test. The key piece of information is the prob column, which shows the p-value. In this case, the probability is 0.004. Since 0.004 is less than our conventional significance level of 0.05, we reject the null hypothesis. Rejecting the null hypothesis means that the unobserved individual effects are correlated with our explanatory x variables. Therefore, the random effects model would be inconsistent, and we must use the fixed effects model to obtain unbiased and consistent estimates. The verdict is clear. If the p-value is low, the random, unobserved effects are correlated with your x variables. Conclusion: you must use fixed effects to avoid bias. This slide introduces Case Study 2, focusing on the difference in difference, or DID method. We see an EViews dialog box for equation estimation, showing the DID method selected, with EMP-tot as the outcome and new min as the treatment variable. The parallel trends graph visually represents the core assumption of DID. It illustrates that before the intervention, both the treatment and control groups follow similar trends. After the intervention, the treatment group's trend diverges, showing the policy effect. Finally, the text on the right highlights key aspects of DID in EViews. EViews automates the calculation of the interaction term. Crucially, we must verify the parallel trends assumption. In EViews, this is done by looking for the parallel trends test, often a wall test, in the output. If the p-value for this test is greater than 0.05, it indicates that the parallel trends assumption holds, validating the DID model. When working with macro panels, which typically have a long time dimension, t, we must be concerned with the time series properties of our data, specifically stationarity. If variables like GDP or consumption are non-stationary, they contain a unit root, and running standard regressions can lead to spurious or nonsensical results. We use panel unit root tests, such as the Levin, Lin, and Shu test, or the Im, Pasarin, and Shin test, to check for stationarity in our panel data. If variables are non-stationary but move together in the long run, they may be co-integrated. The Padroni test extends the concept of co-integration from time series to panel data, allowing us to test for stable long-run relationships. These diagnostic steps are crucial, especially when dealing with panels that have a large number of time observations, typically more than 20 years, to ensure the validity and reliability of our regression results. This slide introduces crucial aspects of panel data analysis, understanding covariance, and testing for causality. The panel covariance matrix on the left visualizes relationships, distinguishing between within correlations and between correlations, as well as individual variances. This helps us see how variables covary both within each panel unit and across different panel units. On the right, we delve into Granger causality tests, which help determine if one variable truly causes another. We have options like the stacked test for common coefficients across panels and the more advanced Dumitrescu-Hurlin test for panels with heterogeneous dynamics. The exploration sidebar reinforces these points. First, visualize covariance relationships, both within and between, before proceeding with regression. Then, when investigating causality, consider whether X causes Y or vice versa, and use the Dumitrescu-Hurlin test when panels exhibit different dynamic behaviors. To summarize, let's look at the essential workflow and best practices for panel data analysis. First, always structure your data correctly, defining both the cross-section and time series IDs. Then, visualize your data to understand its characteristics. Next, test your assumptions to choose the appropriate model, comparing pooled, fixed effects, and random effects, often using the Hausman test. After selecting the model, proceed with the estimation. Finally, validate your results with relevant diagnostics. Key do's include correctly structuring your workfile, comparing models with the Hausman test, and using robust standard errors, such as white period standard errors. A crucial don't is to never ignore cross-section dependence, especially when working with macro panels, as this can lead to biased inferences. Thank you for joining our presentation today. We hope you found the session informative. We believe that data is just a click away. Insight requires the right method. We encourage you to visit our website at www.viatlod.com and our YouTube channel at youtube.com/user/viatlod for more